Okay, it's time to talk about something very exciting. And actually, it's two things that are very exciting. The first one is the symmetric groups, and the second one is the dihedral groups. Um, so these are two really important examples of groups, and we're going to interrogate them maybe in a bit more depth than we have our previous examples. In fact, this whole video will be dedicated to just these two examples. So let's get started. So yeah, we'll do the symmetric groups first, and then what we're going to do, we're going to consider the dihedral group of order 8, which is really about the geometry of a square. Okay, so let's start with the symmetric groups. So let's let omega be some non-empty set, and let S omega be the set of all bijections from omega to itself. Well, then S omega forms a group, and the law of composition is just ordinary composition of functions. The identity is just the identity map. Every map has an inverse because all the maps are bijections. That's pretty obvious. And we call the elements of S omega the permutations of omega because they, in essence, they permute the set omega's elements. And we call S omega itself the symmetric group on the set omega. Okay. So now we didn't really specify any criteria on omega, and that's fine because, you know, we could even let omega be the set of all real numbers or something. But what if it's a finite set? So in particular, let's hone in on omega equals in bracket, which I borrowed this notation from combinatorialists. I believe it shows up in the combinatorics book by Stanley, Enumerative Combinatorics. And by this in bracket, we just mean the set containing the numbers up to n. So n being some positive integer. And in this case, we denote S omega by just S lowercase n, or S subscript n, and we call Sn the symmetric group on n elements. Okay, so we've kind of gotten more specific here. Now we're considering finite symmetric groups. And what we can do, we can actually show that this group has an easily computed order. In fact, the order of Sn is just n factorial. And to prove this, what we do, we just count the number of bijections from n bracket to n bracket. So say we have some arbitrary bijection sigma. Well, sigma of 1, it has to be some number between 1 and n. 1, 2, 3, all the way up to n. So there's n possibilities. Okay, but once we've fixed sigma of 1, the fact that this function's a bijection, that means that sigma of 2, well, it's still going to be some number 1, 2, 3, up to n, but now we've ruled out sigma of 1. So in fact, there's only n minus 1 choices remaining. We can continue. So sigma of 3, well, now we've actually outlawed 2 choices. So there's n minus 2 choices at this stage. And we continue this all the way to the last step. So sigma of n minus 1, well, now there are 2 elements remaining. And sigma of n, everything has been sent to some distinct element except for n. So we have 1 choice. So this is kind of a counting argument. And then what we do, again, this only works because sigma is a bijection. And we take the product of the number of choices at each step. So we have n times n minus 1 times n minus 2, all the way down to times 2 times 1, which is n factorial permutations of n bracket. So the order of Sn is indeed n factorial. Very cool. Now, given a permutation sigma in Sn, we could write out like sigma of 1 is some number, sigma of 2 is another number, etc. But the problem is that it gets tedious and it takes up a lot of space. So we want something more compact. And what we do, we introduce this thing called cycle notation, or a cycle decomposition for sigma. So by a cycle, we just mean some string of integers that cyclically permutes those integers and fixes all the other integers. So in particular, the cycle A1, A2, A3, all the way up to AM, it represents the permutation that sends A1 to A2, A2 to A3, all the way up to AM minus 1 is sent to AM, and then AM gets sent back to the start to A1. Okay, so each AI maps to AI plus 1, and then AM gets mapped just to A1. Now we can have a product of cycles that are just written next to each other, in which case we work from right to left. That might sound weird, but remember this is like we're in this essence interested in doing composition of functions here. That's why we do that, because we compose functions from right to left. So for some general permutation sigma in Sn, the numbers in n bracket will be grouped into cycles as follows. So A1, A2, up to AM1, it will form some cycle, and then we will have AM1 plus 1, AM1 plus 2, all the way up to A sub M2. And we'll keep going until we have used up all the numbers between 1 and n and grouped them into cycles. And it's important to note that we can always write this so that each of these integers between 1 and n appears in exactly one cycle. So in essence, the cycles will be disjoint. And so if we want to determine like the action of our function sigma on the number I, what we do, we find the number I in this expression here, and then we read the number to the right of it. If I is like at the end of the parentheses, before the parentheses, well then I gets sent back to the first entry of the cycle. Let's see. Let's consider this example. So I've given you this permutation sigma belonging to S8, and I've told you that it has this cycle notation. 217 end parentheses, 5, and then finally 8463. And what I want the viewer to do is to try and determine sigma of I for each I between 1 and 8. So you should feel free to pause the video and give this a stab, and then we'll come back. Okay, so here's the solution to this example. So remember, to find how sigma acts on each of the numbers, we find that number in the cycle decomposition and read the number to its right within the same cycle. So sigma of 1 is 7, because we find 1 and it's to the right. Sigma of 2, well, that's going to be 1. Sigma of 3, well, 3 is at the right end of a cycle, so it gets thrown back to 8, so sigma of 3 will be 8. Sigma of 4, we just read to the right, it's 6. Sigma of 5, well, 5 is in a cycle by itself, so 5 is actually fixed by our bijection. So sigma of 5 is 5. Sigma of 6 is 3. Sigma of 7, 7 gets sent back to 2. And sigma of 8 is 4. Okay, so that's not too bad. And what I have here, I have an algorithm that you can use. So given like some permutation sigma in Sn, such that we have sigma of I specified for each I between 1 and n, we can actually determine the cycle decomposition of sigma using this algorithm. So what we do first, we pick the smallest element of n bracket that hasn't appeared in a previous cycle and begin a new cycle with this element. Let's just call that element A. So we start a new cycle that has A. And to the right of that element, A from step 1, you should write sigma of A. So A gets mapped to sigma of A. So that should come to the right. If sigma of A is A, then instead you just close the cycle, and you just have a cycle just containing A, and you return to step 1. Now, read off sigma of A, and write it next in the cycle, or if sigma of A equals A, then we can close the cycle and return back to step 1. And we repeat this step until the cycle closes, until we have formed a loop. And what we want to do, we want afterwards to remove any cycles of length 1, since those really hold no information. So if you think about it here, we could just leave out the 5 because, well, if a number doesn't appear here, it just would mean it's fixed. So this is a convenience of notation. So we remove the 1 cycles. And just as an example of how we can use this algorithm 40, what we would do, like say we have this tau, where tau of 1 is 7, tau of 2 is 4, tau of 3 is 3 itself, etc. What I want you to do is to try and determine its cycle decomposition using the algorithm on the previous slide. So pause the video if you want and come take a stab at it. Okay, so first thing we're going to do, we start at step 1 of the algorithm, and we note that tau of 1 is 7. So we start with 1, 7. And now tau of 7 is 2, so we have 1, 7, 2. And now we just keep going. So tau of 2 is 4, tau of 4 is 10, tau of 10 is 6, etc. until we finally see tau of 5 is 1. And then the first cycle just becomes this list of elements. Now the first number that's not in this cycle is 3. So we start another cycle with 3. But tau of 3 is just 3. So we just have a 1 cycle. Similarly, we have a 1 cycle 9. And we've used all the numbers. So we have this. And then we remove the 1 cycles. So this is our answer. This is how you do a cycle decomposition of that permutation. Now, one nice thing about cycle decomposition is that it actually makes it really easy to compute. So if we have some permutation sigma, well, we can compute its inverse by just reversing the order of the numbers within each cycle of sigma. You should be able to convince yourself that this is true. So for instance, the inverse of this is just gotten by reading each cycle backwards. So 1, 3, 4, 7 gets sent to 7, 4, 3, 1. And 2, 9, 6 just becomes 6, 9, 2. Similarly, we can compute products in cycle notation from right to left again by following elements under the successive permutations. So by sigma tau, we really mean sigma composed with tau. So say we have sigma is the cycle 1, 2, 3, and tau is 1, 2 cycle, 3, 4 cycle. Well, then sigma composed with tau is just this amalgamation of cycles, but we think about it. Well, 1 gets sent to 2, but then 2 gets sent to 3. Okay, so we have 1, 3. Well, now 3 gets sent to 4, and 4 stays there for now, and then 4 gets sent back to 1. So we're good, because 4 gets sent to 3, and then 3 gets sent back to 1, and the successive run through of the cycle. And then 2 forms a 1 cycle, because 2 gets sent to 1, which gets sent back to 2. So we dropped the 2, and it's 1, 3, 4 is the cycle that we're left with. Very good. So, a question for the viewer. If we fix some natural number n, is the symmetric group on n elements abelian? And don't worry too much about this one. Think through it for a second. Maybe you can come up with a nice counterexample. Pause if you'd like. Okay. So, well, if n equals 2, then Sn is abelian. And if n equals 1, then it's also abelian. But if n is greater than or equal to 3, then Sn is non-abelian. And we have a really simple example that just uses cycles involving 1, 2, and 3. So 1, 2 composed with 1, 3 gives us 1, 3, 2, as you can check. But if we reverse the order of these, 1, 3 composed with 1, 2, well, now we get 1, 2, 3, which is different from this. So this shows that in general, cycles do not commute. So you have to be really careful here. However, we do see that disjoint cycles commute. So as long as two numbers aren't shared between any cycles, we can reverse the order of those cycles. So we will see symmetric groups again and again in a few places that maybe will surprise the viewer. Okay. Now, for our second class of examples today, we're going to talk about geometry a little bit. So this is a fun topic because, you know, we kind of get to put our pens down a little bit, or maybe pick them up, but draw some pictures instead of just compute. So consider a rigid square in the plane where the vertices are labeled like I have here, 1, 2, 3, and 4. And by rigid, I really just mean you can't deform the square, you can't cut it, you can't do anything like that, right? It's always going to be a square of the same size. So by a symmetry of a rigid shape, we just mean any action that you can take on the shape which leaves that shape apparently unchanged. So in particular, we might like lift the shape up out of the plane. Like you can imagine if we'd like cut this out really carefully, we could lift it up, rotate it, and then place it back down on top of the depression that we just created in our page. So, and we can make this precise. So what we'll do, we'll let R denote a clockwise rotation that sends, or that is by 90 degrees, or pi over 2 radians. So in this case, 1 would get sent to where 2 was, 2 would get sent to where 3 was, 3 would get sent to where 4 was, and 4 would get sent to where 1 was. And we call this symmetry R. Note that this clearly fits our definition of a symmetry, right? Aside from our labeling, the shape is apparently unchanged, aside from the fact that, you know, I drew this square by hand. So it's not a perfect drawing, but, you know, if it was a perfect square, the argument would hold. And we call this symmetry R. And you could think about like, well, where are we going with this? Well, say we rotated the square twice. Well, now we'd have R squared, which sends 1 to where 3 was, 2 to where 4 was, 3 to where 1 was, and 4 to where 2 was. And we could do it 3 times, 4 times, 5 times, although not all of these are going to be distinct. Because if you rotate this thing 4 times, well, 1 is going to go back to where 1 was, 2 is going to go back to where 2 was, 3 is going to go back to where 3 was, and 4 is going to go back to where 4 was. Okay. So it's possible to obtain symmetries by rotating the square, but we can also obtain symmetries by flipping the square across the diagonal. Look at this typo. Isn't that cute? So let S denote the action of flipping R square across its principal diagonal, by which we just mean this diagonal from the top left to the bottom right. So this will fix all the points on the diagonal, but reflect all the points that don't lie on the diagonal. So in this case, 2 and 4 are fixed vertices, and what we do, we pick up our square and flip it across this diagonal so that it actually interchanges the vertices 1 and 3. And we call this action S. And again, this leaves our square apparently unchanged, like it's upside down, but that's fine. And in particular, the ordering of the vertices has been reversed. So we used to go 1, 2, 3, 4 clockwise, but now we go 1, 4, 3, 2 clockwise. But that's okay. The labelings of the vertices are really just like a bookkeeping tool. So it shouldn't be a surprise. The symmetries of a square form a group, and the operation is composition. So when we talked about R squared earlier, we really meant R composed with R itself again. And this sends 1 to 3, 2 to 4, 3 to 1, and 4 to 2, as I said. Now, again, recall that compositions are computed from right to left. This becomes important because what if SR is not the same as RS? So we read from right to left because this is a composition. And what we have is that the identity is E, of course. We always denote the identity with that. But that's R to the 4th is actually the identity. So the order of R is actually going to be 4. And, you know, we can think of that geometrically, right? If we rotate the square 4 times by a quarter of a rotation, we should get back where we started. Similarly, if we flip the square twice along the same axis, we should get back what we started. So S squared will also be the identity. So the order of S is 2, and the order of R is 4 here. So that's a good thing to note. And the inverse of R, well, we can write R times R cubed here is E. So that means the inverse of R should just be R cubed, and the inverse of S is just S itself, since the order of S is 2. And the group of symmetries of the square, we claim it has order 8. And we denote this group D8, and we call it the dihedral group of order 8. It's worth noting, some people call this group D4, which makes sense because a square has 4 sides, but we call it D8 because it has 8 elements. So whenever you're reading a text, you should be really careful and make sure you understand the established notation that it's using. All right, and we're going to show that the order of D8 is 8, and we're not going to use like anything group theoretic to do this. We're going to use geometry. In particular, we're going to apply the rigidity constraint. So no matter what symmetry we apply, the vertex labeled 1 is always going to be next to vertices 2 and 4. You can see that here. 1 is next to 2 and 4. And you can see that here, where after applying this other symmetry, 1 is next to 2 and 4. And the reason we have that is because of rigidity. If we could violate that, then clearly this thing isn't rigid. So a given symmetry, consider some arbitrary one, it will send the vertex 1 to one of 4 possible positions where one of the previous 4 vertices sat. And once we fix the position of vertex 1 under our symmetry, well, vertex 2, it either lies directly clockwise or counterclockwise relative to vertex 1. So there's 2 possibilities there. So we have 4 times 2, which is 8 possibilities. And we can easily obtain each of these 8 possibilities as a combination of R and S. So each of these corresponds to a valid symmetry. It turns out, as a set, D8 contains the identity symmetry, which just sends each vertex to itself. R r squared, r cubed, s, sr, sr squared, and sr cubed. So in particular, we proved that the order of D8 is 8 using only geometric means, and we didn't even really use any facts about D8 as a group. As a good exercise, you could draw out all of these symmetries and think about how they permute the vertices. Note now that D8 is non-abelian. So to see this, let's just compute SR and RS. So SR, well, we compute R first, and we get this action on R square. And then we apply S to this resulting position that we have, and we get this setup. And now, let's compute RS. So we compute S first. We flip along this principal diagonal, and then we rotate clockwise by pi over 2, and we get this configuration. But these two are clearly not the same. Like here we have 1, and here we have 3. So this doesn't do. So these are not the same. In fact, you could easily verify this yourself if you want. RS equals SR cubed. So I think it's a good time to think about this. Like, you know, we've kind of argued things geometrically in this part. And what we would like to say is that D8 is generated by these symmetries R and S, along with these relations that kind of describe how they act. So in particular, I mean, R to the fourth equals S squared, and both of those are equal to the identity. And we have, as we said on the previous slide, RS equals SR cubed. And it turns out from these we can actually simplify any expression involving R and S in D8. So in particular, these tell us how to simplify expressions that involve both R and S. So for example, we could prove that SR equals R cubed S. So RS equals SR cubed. Well, we were given this. If and only if we multiply on the right of each side by S. But this gives S squared, which is just the identity, so we can get rid of that. And we just have R equals SR cubed S. Now we left multiply by S on each of these, and we get SR equals S squared R cubed S. But S squared again is just the identity, so we're left with SR equals R cubed S. Very nice. And just a final example for people to work through. Say I give you in D8 this expression that looks kind of monstrous. Not too monstrous, but a little bit. SR cubed, S to the sixth, R to the ninth, S cubed. And what you're supposed to do, what I want the viewer to try and do, is simplify this to an expression of the form S to the I, R to the j, for some I between 0 and 1, and some j between 0 and 3. So pause the video and try to simplify this using just these two relations. And I guess this one if you want, since we did derive that. Pause it and give it a shot. Okay. So in particular, what we can observe to start with is that S to the sixth, well, that's S squared cubed. But S squared is just the identity E. So S to the sixth is just E cubed. But that's just E. It's the identity. Similarly, this R to the ninth, well, that's R, and then we can factor out R to the fourth squared, which just becomes E squared. So r to the 9th is actually just r. And you can think of this geometrically, right? If you flip the square 6 times on the same axis, you should get back what you started. And if you rotate it by a quarter of a square 9 times, well, you go back to where you started twice, and then you go an additional quarter turn. So rotating a quarter turn 9 times is equivalent to rotating 1/4 turn. Okay, so in particular, this simplifies just to SR cubed times R times S cubed. But hold up, R cubed R is just R to the 4th, which is E. So this actually, the middle drops out, and now we have S times S cubed. Well, that's just S to the 4th. Similar to the argument above, that's S squared squared, which is E squared, which is just E. And I guess like to completely fulfill the assignment, we should write this as S to the 0 times R to the 0, but we don't really need to. So the importance is, like, we can simplify this seemingly hideous thing quite a lot. In fact, we simplified it just to the identity, so that's kind of cool. Okay, so today we saw a couple of really nice examples of non-abelian groups. And I think it's like worth pointing out the fact that the groups that we were considering weren't groups of numbers or anything like that. They were actually groups whose elements were objects that were acting on some other set of objects. So for example, like when we introduced the symmetric groups, the elements weren't numbers. They were functions that send numbers to other numbers. Or when we talked about the dihedral group of order 8, the elements weren't the vertices of a square. Rather, they were functions that sent the vertices of a square to other positions. And this concept of an action of a group or another algebraic structure acting on another set turns out it's going to be really important, and we're going to spend a lot of time on this. So in the next video, it will be a problem-solving video with many worked problems, maybe 5 or 6 problems. And then the next main sequence video, number 6, what we'll do, we will further explore the concept that we kind of were hinting at, where we claimed that we can kind of generate D8 from these elements R and S, along with like some relations that they obey. And we're also going to talk about generalizing from the symmetries of a square to maybe the symmetries of like an arbitrary polygon. So rather than D8, we'll have D2n, where n is the number of sides on our regular n-gon. All right, thank you for viewing this video, and I will try to have another video up soon.